Where are your keys right now? In your pocket, on the table, in the bag by the door, somewhere. You might not know where, but they're somewhere. That's not even a belief you hold consciously. It's more basic than that. It's the assumption underneath every belief you have about the physical world. Things are somewhere, one place, always. The universe disagrees. A single atom, one atom, under controlled laboratory conditions, has been shown to pass through two separate openings simultaneously, interfere with its own other path, and arrive as a single particle at a detector on the other side. Not a simulation, not a theoretical prediction we're still waiting to test. Done, measured, published. The atom was in two places at once, and the interference pattern it left behind is the proof. I want to walk you through exactly how we know this, not the watered-down version, the real one, with the precision it deserves and the honesty to admit where the mystery doesn't resolve. Start with a wall, a barrier with two narrow slits in it. Behind the barrier, a detector screen. Now fire something at the slits, light, say. What do you expect to see on the screen? If light is a stream of particles, you'd expect two bright bands, one behind each slit. Simple geometry. The light goes through one opening or the other and lands in a corresponding spot. What you actually see is this, a series of alternating bright and dark stripes spread across the screen. Many bands, not two. Bright where light accumulates, dark where it doesn't, in places where, by particle logic, some light should have landed. This is an interference pattern, the kind you get when waves overlap. When the peak of one wave meets the trough of another, they cancel. That's why the dark bands exist. The light is cancelling itself. So light behaves like a wave. Fine. That was Thomas Young in 1801, and it took a while to fully accept, but eventually it became standard physics. Here's where it gets uncomfortable. Do the same experiment with electrons. Fire electrons, particles, not waves, with mass and charge and a definite size, one at a time at the same kind of barrier. One electron at a time, no overlap, no interaction between electrons, just one, then another, each one detected individually as a single point on the screen. Build up the pattern over thousands of electrons. What do you get? The same interference pattern, bright and dark stripes, the same wave signature, from particles fired one at a time with nothing to interfere with, except themselves. Each electron went through both slits, interfered with its own other path, arrived as a point. The pattern on the screen only makes sense if each individual electron passed through both openings simultaneously and then interfered with itself on the other side. There is no other explanation that fits the data. People have tried. The alternatives all fail. And then it was done with atoms. Whole atoms, hydrogen, then heavier ones, showing the same behavior. And then molecules, buckyballs, molecules made of 60 carbon atoms bonded into a tiny soccer ball shape, fired through an interferometer by Anton Zeilinger's group in Vienna in 1999, producing interference fringes. A molecule of 60 atoms in two places at once, self-interfering. The result published, replicated, extended. Since then, the record has been pushed to molecules containing more than 2,000 atoms. The interference persists, the superposition persists. The weirdness doesn't go away when the object gets bigger. It just becomes harder to preserve for reasons we'll get to. Now, the word for what the atom is doing, the technical term, is superposition. It exists in a superposition of both paths, both positions, both possibilities simultaneously, described mathematically by something called a wave function that spreads across both locations at once. I want to be careful here because the word superposition has a way of making people feel like they've understood something when they've only labeled it. Let me tell you what superposition is and, equally important, what it isn't. It is not the atom is in one place and we just don't know which one. That would be an ordinary problem of ignorance. We don't know where your keys are, but they're somewhere. That's not what's happening with the atom. The atom doesn't have a definite position, not hidden from us, not determined but unknown, genuinely, physically indeterminate, until it's measured. How do we know it's not just ignorance? Because of the interference pattern. If the atom was secretly going through one slit all along, we just didn't know which, then half the atoms go through the left slit, half through the right, and they pile up in two bands. No interference. The interference pattern is only possible if both paths are simultaneously real, both contributing to the atom's evolution, because only then does the cancellation and reinforcement that produces the stripes actually occur. The wave function isn't a map of our ignorance. It's a description of the atom's actual physical state. Both paths are real in the sense that both affect what happens. That's what superposition means when you don't let the word do the work for you. Here's the weird part. Add a detector to one of the slits, something that tells you which path the atom took, just a passive observer recording the information, not blocking anything. The atom still passes, but now the interference pattern disappears completely. Two bands, classical behavior, exactly as if the atom had always been going through one slit all along. The act of gaining the information, making the which path knowledge available anywhere in the universe, destroys the superposition. The atom, having been watched, no longer explores both paths, it picks one. And this is one of the most disturbing things in all of physics. Not because it's confusing, physicists have learned to work with it, but because it has no satisfying explanation. Why does measurement change the outcome? What exactly counts as a measurement? Does it need to be a human, a detector, any interaction with any other particle? The equations, the Schrödinger equation, the Born rule, give us exact, precise predictions. They work. Every experiment confirms them. But the equations themselves don't tell us why observation collapses the wave function, or what collapse even physically means. This is called the measurement problem, and it is not a solved problem. It is one of the deepest open questions in all of foundational physics. Different interpretations of quantum mechanics take different positions. The Copenhagen interpretation, the standard textbook version, says the wave function is a calculational tool, not a real physical thing, and collapse is just the update of our knowledge. It's pragmatic, it works, it doesn't explain anything. The many worlds interpretation says the wave function is real and never collapses. Instead, the universe branches. Every possible outcome happens in a different branch of reality. The atom went through both slits in different branches, and you, the observer, split into two versions, one for each outcome. This is mathematically consistent. It's also almost impossible to accept emotionally, and raises difficult questions about what probability even means when everything happens. There are other interpretations: pilot wave theory, relational quantum mechanics, cubism. They all reproduce the same experimental predictions. They disagree, sometimes radically, about what's actually happening. We don't know which, if any, is correct. This is not ignorance we expect to resolve next year. It's a genuine, unresolved, conceptual problem that some of the best physicists in the world have spent decades arguing about. I think it's important to sit with that, not to use it as an excuse to get mystical or start importing ideas from outside science, but to be honest. The most successful scientific theory in history, quantum mechanics, accurate to more decimal places than any other theory we have, operates on foundations that remain philosophically unsettled. That's remarkable. Now let me tell you why superposition doesn't seem to apply to large objects, why your keys are in fact in one place and won't be found in two. The answer is decoherence. When a quantum system, an atom, a molecule, interacts with its environment, it becomes entangled with it. Every air molecule that bounces off it, every photon that scatters from it, every tiny interaction with the surrounding world carries away a little information about the system's state. That information leakage is what destroys superposition. It doesn't collapse the wave function in a philosophically dramatic way. It just spreads the quantum state across so many degrees of freedom in the environment that the interference terms become unmeasurably small, effectively zero, extremely fast. For a single atom in a vacuum kept isolated, the decoherence time is long enough that we can observe the superposition. For a buckyball, it's shorter. The molecule is bigger, interacts with more of the environment, and you need to work harder to isolate it. For a dust particle, it's on the order of fractions of a nanosecond. For a marble, it's so absurdly short, something like 10 to the minus 36 seconds, that no measurement in principle could ever catch it in superposition. The decoherence is, for all practical purposes, instant. That's why we don't see cats in superposition, not because quantum mechanics stops applying, because the environment constantly, irreversibly, catastrophically entangles with everything large enough to interact with it. The quantum behavior is still there. It just becomes invisible, washed out by the noise of every surrounding particle. But, and this is the frontier, decoherence explains why we can't observe large-scale superposition. It doesn't necessarily explain why the classical world we experience is the only outcome. In many worlds, the other branches are still there. In Copenhagen, the question is avoided. In other interpretations, it's handled differently. The boundary between quantum and classical, if there even is a sharp boundary, remains an active area of experimental and theoretical research. Groups around the world are now trying to put larger and larger objects into superposition states. Nanoscale mechanical oscillators, cooled to their quantum ground state, have been placed in superpositions of different vibrational modes, objects you can almost see with the naked eye in quantum states. The goal is to keep pushing, to find the limit if there is one, or to confirm there isn't one if there isn't. And then there's the application side. Quantum computers use superposition directly. A classical bit is 0 or 1. A qubit, a quantum bit, can be in a superposition of 0 and 1 simultaneously. 2 qubits can be in a superposition of 4 states at once. The number of simultaneous states scales exponentially with the number of qubits. That's what gives quantum computers their potential, not speed in the conventional sense, but the ability to process exponentially many possibilities in parallel, because the hardware is, physically, doing all of them at once. Quantum cryptography uses superposition to create provably secure communication. Eavesdropping disturbs the quantum state in a detectable way because measurement changes the system. Quantum sensing uses it to build accelerometers, gravimeters, and clocks of extraordinary precision. The same physics that makes atoms behave strangely in double-slit experiments is the physics that is, right now, being engineered into devices that will change how we compute, communicate, and measure. None of that would be possible if the atom just picked a slit and stayed in it. So let me bring it back to where we started. You have an assumption built into your experience of the world that things are somewhere, one place. And that assumption works. It works so well for every scale of experience you've ever had that you've probably never questioned it. It's not a bias you picked up. It's a conclusion your brain drew, correctly, from every piece of evidence your senses have ever given you. The evidence your senses give you is just incomplete. It comes from the classical limit, the large-scale, room temperature, air-filled, light-saturated world where decoherence is so fast and so total that quantum superposition is invisible. Your brain built its model of reality from that evidence and got the physics of keys and tables exactly right. But the same model, applied one level down to the atoms those keys and tables are made of, is simply wrong. The atom was in 2 places, not because the physics is exotic or theoretical, because that's what atoms do. The double-slit experiment isn't an anomaly we need to explain away. It's a window, and what it shows us is that the layer of reality beneath the one we experience doesn't work the way we assumed. We have equations that predict it with perfect accuracy. We have experiments that have confirmed it with extraordinary precision. We have technology built on it. And we still don't fully understand what it means, what is actually happening when an atom exists in 2 places, and why the act of looking forces it to choose one. That's not a gap we expect to close with more data alone. It's a conceptual gap, a gap between prediction and understanding, between naming a thing and knowing what the thing is. I've spent a great deal of time thinking about what reality is made of, and the honest answer, the one I keep coming back to, is this. Whatever reality is made of, it is not made of things that are somewhere. It's made of something that has location only when asked, only when the universe interacts with itself in the right way and produces, as an outcome, what we call a particle in a place. The rest of the time, it's doing something else entirely, something we can calculate perfectly and understand only dimly. The atom was in 2 places at once, proven. And the most unsettling thing about that isn't the fact. It's that the fact has been known for nearly a century. And the question it raises about what reality actually is has never been answered.